Force, in its simplest form, is the engine of change in the physical world. Whether a raindrop carves stone over centuries or an avalanche reshapes a mountain in moments, the manner in which energy is gathered and delivered determines the magnitude of its effect. The principle of concentration of force arises from this observation, that power, when focused rather than dispersed, achieves results far greater than the sum of its parts. In physics, this principle governs collisions, explosions, and the transfer of momentum. In nature, it drives the predatory strike, the tectonic upheaval, and the cellular machinery of life. Across centuries, strategists and engineers alike have sought to harness concentrated force, transforming the course of battles and the efficiency of machines. To understand this principle is to see the world anew, tracing the quiet logic that underpins both destruction and creation, both natural phenomena and human innovation. When we speak of force, we invoke a concept at the very heart of physics and engineering. Force is the invisible hand shaping the universe, mediating interactions between objects both great and small. But before we can appreciate the power that comes from concentrating force, we must first unravel what force actually is, how it behaves, and why its careful application changes the course of history and the nature of reality itself. In classical mechanics, force is defined as the physical entity that mediates interactions between objects. This definition, rooted in Newton's laws, remains foundational even as our understanding of the universe has expanded from the tangible to the subatomic. Newton's laws, especially the second law, set the stage. The acceleration of an object is directly proportional to the net force acting upon it and inversely proportional to its mass. If an object changes its motion, a force is at play. This simple yet profound relationship tells us that acceleration always signals the presence of a force, and that force is not an abstract notion but a measurable, directional quantity, a vector pointing the way in which it acts. But force is more than just a push or pull. It is the language by which the universe communicates, whether through the steady pull of gravity, the snap of a stretched rubber band, or the strength holding the nucleus of an atom together. In the language of physics, force is closely related to momentum and energy, two other pillars upon which the edifice of mechanics is built. Momentum, also a vector, is the product of an object's mass and its velocity, a measure of how much motion it carries. When a force acts on an object, it changes its momentum. This transfer is the essence of a force's action. Energy, in contrast, is a scalar, a number without direction that quantifies the capacity to do work. When forces move objects, energy is transferred or transformed, always according to the strict bookkeeping that physics demands. To ground these concepts, consider how classical physics approaches the central force problem, a scenario where an object is influenced by a force directed always toward or away from a central point. Gravity is the prime example. The pull between the Earth and the Moon, or the Sun and its planets, is a central force, drawing bodies together along the line that connects their centers. Electromagnetism, too, fits this pattern, with charged particles attracted or repelled along a similar axis. These forces are not distributed haphazardly but act with remarkable focus, enabling the stable orbits of planets and the predictable patterns of atomic structure. The universe, it turns out, is governed by just four fundamental forces. Gravity sculpts galaxies and tugs at every mass. Electromagnetism binds atoms and lights our world. The strong nuclear force holds protons and neutrons in the heart of atoms, and the weak nuclear force is responsible for certain types of radioactive decay. Each of these acts in its own domain, with distinctive strengths and ranges. Gravity, despite its cosmic reach, is much weaker compared to the strong nuclear force, which dominates at subatomic distances but fades rapidly beyond the tiniest scales. Electromagnetism is familiar and versatile, responsible for everything from lightning to the structure of molecules. The weak force, subtle yet essential, quietly shapes the behavior of matter through processes often invisible to the naked eye. When we talk about the concentration of force, we are describing the deliberate or natural focusing of this fundamental power. In physics, forces can be distributed across an area or focused at a point, an idea that finds practical application in countless settings, from the tip of a needle to the point of a spear. Engineers, when analyzing structures, often simplify distributed forces as point forces for ease of calculation, allowing them to predict how beams will bend, bridges will hold, or machines will function. The reason is straightforward. Concentrated force, when applied to a smaller area, can produce dramatic effects, a concept that echoes through both human invention and the workings of nature. But what does it mean to concentrate force? In everyday terms, it involves gathering available power into a focused effort, whether that effort is the sharp impact of a hammer blow, the thrust of a rocket engine, or the coordinated advance of troops in battle. In physics, this focusing often involves manipulating the direction, magnitude, and point of application of force to maximize its effect. For instance, when you drive a nail with a hammer, the force delivered is momentarily concentrated on the tiny tip of the nail, allowing it to penetrate wood. The same principle is at work in the cutting edge of a knife, the narrowed barrel of a cannon, or the pointed prow of a ship breaking through water. The efficacy of concentrated force is rooted in its relationship with momentum and energy. When a force acts on an object over a period of time, it imparts momentum. This is the impulse. The greater the force and the longer it acts, the more momentum is transferred. This concept is not just an abstraction, it is the reason why a fast-moving baseball can shatter a window or why a slow but heavy freight train takes so long to stop. Energy, meanwhile, tells us how much work can be done by that force. A force moving an object through a distance does work, transferring energy from one form to another. The concentration of force, therefore, is about maximizing the transfer of momentum and the efficient use of energy to achieve a specific outcome. In the natural world, the concentration of force is everywhere. The jaws of a crocodile, closing with tremendous power at the tips of its teeth, demonstrate how evolution has honed the application of force for survival. In the human-built world, the design of tools and weapons often reflects an understanding, sometimes intuitive, sometimes scientific, of the power that comes from focusing force. The ancient catapult, the modern hydraulic press, and the surgical scalpel all rely on this principle. As physics has progressed, our conception of force has also evolved. The 19th century saw the rise of field theory as scientists like Faraday and Maxwell expanded the idea of force beyond the immediate contact of object on object. Forces could now be understood as manifestations of fields, entities that extend through space, influencing objects at a distance. Gravity and electromagnetism, in particular, are now seen not just as forces but as fields, with their own dynamics and behaviors. This insight opened the door to a deeper understanding of how force operates not just at the human scale, but across the vast stage of the universe and down to the tiniest particles. At the atomic and subatomic levels, the picture grows even more complex. The strong nuclear force, for instance, is the most powerful of all known forces, yet its domain is vanishingly small, confined to the heart of the atom. It holds protons and neutrons together with a grip that dwarfs gravity and electromagnetism, yet it acts only at distances measured in femtometers. The weak nuclear force, though less potent, is essential for processes such as nuclear decay, quietly shaping the age and evolution of matter itself. Measuring and understanding these forces pose significant challenges, as their effects are hidden from everyday experience and require sophisticated tools and theories to probe. Still, at every scale, the principle of concentration of force remains relevant. Whether in the collision of galaxies or the fusing of atomic nuclei, the outcome depends on how force is brought to bear, how it is directed, focused, and unleashed. In engineering and construction, careful analysis of how forces are distributed, concentrated, and resisted is essential for safety and efficiency. For example, the strength of a bridge or a skyscraper depends on the distribution of forces through its structure. Engineers use mathematical models to ensure that these forces are concentrated where materials are strongest and dispersed where they might cause failure. The interplay between force, momentum, and energy is governed by fundamental laws, most notably the conservation of momentum and the conservation of energy. These laws state that in a closed system, the total momentum and energy remain constant unless acted upon by external forces. This is why the direction and magnitude of force matter so much. They determine how and whether momentum and energy flow from one part of a system to another. When external forces are introduced, they can change the motion of objects, transfer momentum, and do work, reshaping the system's behavior in profound ways. In practical terms, understanding the concentration of force allows us to solve problems and harness nature's power. When building machines, designing vehicles, or constructing buildings, engineers must consider how to apply forces efficiently and safely. In sports, athletes intuitively seek to concentrate their effort at the right moment. Think of a sprinter exploding from the starting blocks, or a martial artist delivering a focused strike. Even in the realm of strategy and conflict, the concentration of force, whether physical or metaphorical, can turn the tide of events. The history of science and engineering is, in many ways, a history of learning how to control and focus force. From the simple lever to the particle accelerator, humanity's greatest achievements have often depended on the ability to concentrate power, direct it with precision, and harness its effects for constructive, or, at times, destructive purposes. While our understanding of force has grown more nuanced, with quantum mechanics and field theory adding new layers of complexity, the classical principles remain as true and as useful as ever. The vector nature of force, its ability to change momentum, and its role in transferring energy are the foundation upon which all further understanding is built. As we move forward in this exploration, the principle of concentration of force will serve as a guiding thread, linking the fundamental laws of nature with the practical challenges of the world around us. In the end, whether we are contemplating the orbits of planets, the architecture of bridges, or the split-second decisions of athletes and generals, the concentration of force is a principle that unites the abstract beauty of physics with the tangible realities of life. It reminds us that, by understanding and harnessing the ways in which force can be focused, we unlock possibilities both grand and precise, wielding the power that shapes worlds and the ingenuity that builds them. In the endlessly inventive world of nature and the ever-advancing realm of technology, the principle of concentrating force emerges as both a subtle architect and a bold disruptor. Nature has refined this principle over eons, and humanity, inspired by observation and necessity, has learned to harness it in countless ingenious ways. To understand how this principle shapes the world around us and within us, we must look beyond simple definitions and see how focused force animates processes from the molecular to the planetary, from the smallest cell to the most complex machine. Let us begin with a simple yet profound fact. Pressure measures force distributed over an area. When a given force is applied to a smaller area, the pressure increases dramatically. This relationship, force per unit area, may sound like a formula tucked away in a physics textbook, but its consequences ripple through nearly every corner of the natural and engineered world. In practice, a gentle push when focused to a pinpoint can break through where a broad shove would fail. In engineering, this insight is fundamental. Whether driving a pile into the ground or designing the tip of a hypodermic needle, the effectiveness of a modest force is magnified by narrowing the area over which it acts. This same principle underlies countless tools and echoes through living tissues and geological upheavals alike. Consider how pressure and area combine to define mechanical efficiency. In design and construction, this interplay is not just a matter of elegance but of survival. The choice to concentrate force can mean the difference between a structure that stands for centuries and one that fails at the first sign of strain. Engineers must carefully balance efficiency with durability. A concentrated force can split a rock or drive a fastener, but if not managed wisely, it can also become a point of weakness. This leads us to the concept of stress concentration, a phenomenon that has challenged designers since the dawn of civilization. Stress concentration occurs wherever there is a sudden change in the geometry of a material, at the edge of a hole, the tip of a crack, or the sharp corner of a cutout. These discontinuities focus stress, multiplying the local force far beyond the average experienced elsewhere in the material. As a result, a structure can fail under loads that would be harmless if distributed evenly. The stress concentration factor quantifies this amplification, with values depending on the specific geometry involved. To mitigate this risk, engineers use strategies such as smoothing sharp transitions, introducing fillets, or reinforcing vulnerable regions. These methods are not just technical fixes, they are responses to the fundamental truth that both nature and mechanics reward the careful management of concentrated force. The Earth itself is a stage where the drama of concentrated force unfolds on both grand and gradual scales. Geological forces, those slow, irresistible engines of plate tectonics, continental drift, and volcanism, have shaped the planet's landscape over billions of years. Though vast, these forces often have highly localized effects. The grinding of tectonic plates at a fault line, for example, channels the immense stress of moving continents into a narrow zone. Over centuries, this concentrated force deforms, fractures, and transforms rock, lifting mountains or unleashing earthquakes with sudden, catastrophic release. The study of crustal deformation reveals that applied stresses, when focused along faults or within folds, can lead to dramatic strain, bending, breaking, or even liquefying rock. The efficiency of such transformation lies not in the brute scale of the force, but in its relentless concentration at specific sites. Looking closer, geologists have found that even at the microscopic level, surface forces such as van der Waals interactions influence the behavior of minerals and the cohesion of sediments. While these forces are far weaker than the tectonic stresses that move continents, they are highly significant where they act over minute areas. The measurement and theoretical understanding of such forces continue to inform our grasp of how Earth's materials respond to pressure, friction, and deformation, knowledge that guides fields as diverse as civil engineering and planetary science. Biology, too, is a realm where concentrated force is not only present, but indispensable to life itself. Within living organisms, the shaping of tissues and organs is guided by a complex choreography of mechanobiological forces. During development, cells experience and generate forces that are precisely focused to mold, stretch, and fold tissues into their destined forms. These forces are often subtle and challenging to measure, but their impact is profound. Mechanobiology has begun to reveal how the efficiency and directionality of force application determine not just the shape of organs, but also their function and resilience. In the growing field of regenerative medicine, understanding how to replicate or direct these forces opens new possibilities for engineering tissues that heal or replace those lost to injury or disease. At an even smaller scale, the molecular mechanisms that drive transformation in bacteria offer a striking example of nature's capacity to focus force with exquisite precision. Bacterial transformation, the process by which bacteria take up genetic material from their environment, relies on a suite of molecular machines that manipulate DNA and cell membranes. These processes are governed by forces acting at the nanometer scale, yet their consequences can be transformative for the organism. Scientists have learned to harness these natural mechanisms, adapting them for use in biotechnology and medicine. To increase the efficiency of bacterial transformation, researchers use techniques such as heat shock and electroporation. In heat shock, a sudden increase in temperature makes the cell membrane temporarily permeable, allowing DNA to slip inside. Electroporation, by contrast, applies an electric field across the cell membrane, creating transient pores through which DNA can pass. Both methods exploit the principle of concentrated force. A brief, localized pulse, whether of heat or electricity, alters the membrane in a way that would never occur under uniform, gentle conditions. The success of these techniques has revolutionized genetics, enabling the creation of genetically modified organisms and advancing our ability to understand and manipulate life at its most fundamental level. The historical development and application of bacterial transformation have had far-reaching implications. From early experiments to modern gene editing, the ability to direct and concentrate force at the cellular and molecular level has unlocked new avenues in medicine, agriculture, and environmental science. The efficiency of these processes depends on understanding how to focus energy and force where they are most needed, whether to breach a cell membrane or to integrate new genetic material. The world of human technology is, in many ways, a continuous quest to concentrate force more effectively. In mechanical systems, efficiency is often measured by examining how input force is converted into useful work, with losses due to friction, heat, or deformation carefully accounted for. Engineers strive to design machines that channel force where it will do the most good, minimizing waste and maximizing output. This imperative drives innovation in fields from manufacturing to transportation, where the precise application of force can mean the difference between success and failure. Structural engineering, in particular, is deeply concerned with the effects of stress concentration. The presence of a hole, notch, or abrupt change in a shell or beam can localize force, creating a hotspot of stress that may precipitate failure. Theoretical and practical studies have shown that these effects can be predicted and, to some extent, controlled by careful design. By understanding the distribution of force and the behavior of materials under load, engineers can develop structures that are both strong and efficient, able to withstand the concentrated forces they encounter without succumbing to them. The digital age has propelled the notion of concentrated force into new and often unexpected domains. In modern warfare and defense, the concept has been transformed by technology. Advanced systems now enable forces to be applied with unprecedented precision, speed, and deception. Artificial intelligence, autonomous systems, and cyber warfare represent new mechanisms for concentrating force, not just in the physical sense, but in the ability to deliver effects rapidly and at scale. The battlefield has become a contested terrain where information and technology are as decisive as tanks or missiles. The evolution of modern warfare illustrates how the concentration of force is no longer limited to physical confrontation. Drones and precision weapons can strike specific targets with minimal collateral damage, focusing destructive power exactly where intended. Cyber attacks, meanwhile, concentrate force in the virtual realm, disrupting networks, infrastructure, and communication with carefully targeted actions. These strategies underscore the changing nature of conflict, where the ability to concentrate and redirect force, whether kinetic, digital, or informational, can determine the outcome of engagements and even the fate of nations. Technology's role in shaping defense strategies is similarly rooted in the ability to focus effort, attention, and resources. Network-centric warfare, for example, leverages connectivity and data to concentrate force at critical points, exploiting speed and surprise. The use of artificial intelligence and autonomous platforms further amplifies this effect, enabling rapid decision-making and adaptive responses that maximize efficiency. In this context, the principle of concentrated force is both a tool and a challenge, offering opportunities for innovation while demanding new forms of resilience and security. Across geology, biology, and technology, the mechanisms by which force is concentrated reveal a common thread: the pursuit of efficiency, breakthrough, or transformation. Whether in the slow grinding of tectonic plates, the delicate shaping of organs, the strategic use of stress in engineering, or the precision targeting of modern defense systems, the focused application of force stands as a powerful enabler. Yet, it is also a source of vulnerability, requiring careful control and constant vigilance. Nature and human ingenuity alike have shown that the concentration of force is not just about brute power, but about where, when, and how that power is brought to bear. The efficiency of natural and engineered systems depends on this careful choreography, on knowing how to marshal resources, shape materials, and guide energy to create, transform, or defend. The challenge, as always, is to balance the benefits of concentrated force with the risks it entails, to harness its potential without succumbing to its dangers. In the chapters to come, we will continue to explore how the principle of concentrating force unfolds in ever more complex and surprising ways, shaping the world we inhabit and the future we imagine. For now, it is enough to recognize that from the microcosm of the cell to the macrocosm of society, the focused application of force is both a mechanism and a manifestation, a driving force behind the unfolding story of nature and technology. Concentration of force, as a principle, is as much about timing, coordination, and context as it is about sheer magnitude. In the military domain, it is woven into the fabric of doctrine and decision-making, shaping not only the outcomes of battles, but also the broader trajectory of conflict and, by extension, history itself. At its core, force concentration is the deliberate act of massing combat power at a decisive point, tipping the scales of local superiority and enabling an outnumbered force to prevail against larger, more dispersed opposition. This is not simply a matter of piling on resources or firepower. It demands a nuanced grasp of terrain, technology, organization, and the psychology of both friend and foe. The theoretical roots of this principle span centuries and continents. Clausewitz, Jomini, and Sun Tzu each articulated the necessity of mass at the critical moment, though their interpretations differed in emphasis and application. Clausewitz saw the concentration of force as the center of gravity for decision, where the outcome of an entire campaign might hinge on a single, well-timed blow. Jomini emphasized the importance of interior lines and maneuver, allowing a commander to rapidly shift forces and achieve local superiority. Sun Tzu, centuries earlier, advocated the subtle art of appearing weak when strong and strong when weak, using concentrated effort to confuse and outflank the enemy. These foundational theories have been revisited and adapted as the character of war has changed, but their essential message remains: spreading forces too thin risks defeat in detail, while effective concentration multiplies combat power. The logic of force concentration has proven itself time and again on the battlefield. Historical analyses highlight campaigns such as Blitzkrieg, where German forces during World War II harnessed speed, coordination, and focused armored thrust to shatter more static defenses. In the Pacific Theater, Operation Cartwheel demonstrated how joint forces could converge on a critical objective, isolating and neutralizing enemy strongpoints through synchronized action. These successes underscore the force multiplier effect. By assembling capabilities at the point of decision, armies have achieved results disproportionate to their numbers. Yet as military doctrine has evolved, so too have the challenges and limitations of this approach. Modern joint operations, combining land, sea, air, and increasingly cyber domains, require that the principle of concentration be adapted to new realities. The proliferation of advanced surveillance, precision munitions, and rapid communication means that massing forces in one place can quickly make them vulnerable to detection and destruction. This has fueled a doctrinal shift toward creating the virtues of mass without the vulnerabilities of concentration, as articulated in contemporary force design strategies. Today's planners emphasize mobility, low-signature operations, and the ability to combine dispersed units at the moment of need, leveraging networks and technology to concentrate effects rather than physical formations. The impact of technological innovation on force concentration cannot be overstated. Advances in sensors, communications, and weaponry have redefined what it means to mass power. Where once concentration meant the literal gathering of men and machines, it now often involves the orchestration of information, the synchronization of remote fires, and the agile retasking of assets across vast distances. The emerging future of warfare, as outlined in forward-looking military assessments, envisions a battle space dominated by rapid, decentralized action, where the ability to concentrate effects, whether through kinetic means or through cyber and informational tools, will be decisive. These trends extend beyond the military sphere. The concept of concentrating force resonates in engineering, science, and organizational strategy. In joint operations, for example, success depends not only on the massing of hardware, but on the seamless integration of software and human decision-making. The effectiveness of a force is determined by how well it can combine these elements at the right time and place, overcoming the friction inherent in complex systems. In this sense, force concentration is not merely a physical process, but a systemic one requiring the alignment of goals, resources, and timing for maximum impact. The limitations of the principle are as instructive as its successes. Concentrating force carries inherent risks. Aggressive states have used concentrated power, often by arming proxy groups or non-state actors, to destabilize regions and overwhelm less prepared opponents. For weaker states or coalitions, the challenge is even greater. They must find ways to resist or evade superior concentrations of force, relying on dispersion, deception, or asymmetric tactics. In environments where detection is swift and retaliation is lethal, the classical image of massed armies becomes less relevant. Instead, survivability is achieved through agility and the ability to reconstitute combat power on demand. The adaptation of the concentration principle to modern warfare is also shaped by geography and the physical environment. Terrain, weather, and urban complexity can all constrain the ability to mass forces, forcing commanders to seek alternative avenues for achieving local superiority. The future battlefield, according to current military thinking, will be characterized by contested domains, rapid maneuver, and the need to outpace an adversary's decision cycle. In such contexts, the concentration of force may manifest as a fleeting advantage created by surprise, speed, or superior information, rather than as a sustained physical presence. Doctrinal studies highlight that the nature of force concentration is closely tied to organizational structure and culture. The way a military or engineering team is organized, its hierarchy, communication protocols, and decision-making processes can either facilitate or hinder the effective application of concentrated power. The ability to rapidly assemble and coordinate disparate elements depends not just on technology, but also on training, trust, and shared understanding. In grand strategy, the concentration principle informs not only battlefield tactics, but also the allocation of national resources, the development of alliances, and the pursuit of technological superiority. As new actors and technologies emerge, the landscape of force concentration becomes even more complex. Non-state groups, empowered by access to advanced weapons or cyber capabilities, can achieve effects once reserved for nation-states. The rise of unmanned and autonomous systems introduces further layers of complexity, enabling effects to be concentrated across domains and at unprecedented speeds. The interplay between hardware, software, and human operators is now central to the design of effective force concentration strategies. Looking ahead, the character of warfare in large-scale engineering will continue to evolve in response to these pressures. Future force design, as envisioned by defense thinkers, emphasizes adaptability, creating forces that can generate massed effects when required but are not vulnerable to catastrophic losses if detected or targeted. This involves a blend of mobility, deception, and the use of low-signature technologies, as well as the ability to rapidly disperse and reconcentrate as the situation demands. The concept of networked swarming, where small autonomous units coordinate to achieve mass at the critical point, is one possible direction that draws directly on the enduring logic of force concentration. There are also broader societal implications to consider. The principle of concentrating force, while rooted in military thought, has analogs in fields as varied as project management, crisis response, and scientific research. In each case, the challenge is to marshal resources, whether people, knowledge, or tools, at the moment and place where they will have the greatest effect. The lessons learned from centuries of military and engineering practice offer valuable insights for these domains, highlighting the importance of preparation, coordination, and decisive action. At the same time, there are enduring questions about the ethical and strategic risks associated with concentrated power. The ability to mass effects, whether through military means or through economic or informational leverage, can be a source of instability if not carefully managed. The destabilizing potential of aggressive concentration, especially when combined with emerging technologies, poses challenges for international security and governance. Strategies that balance the benefits of concentrated action with the need for restraint and resilience will be central to future debates. In sum, The principle of concentration of force occupies a unique place at the intersection of science, strategy, and technology. Its theoretical foundations are deep, shaped by generations of thinkers and practitioners who recognize the power of focused effort. Its applications are broad, touching everything from the design of military campaigns to the orchestration of complex systems in engineering and beyond. The benefits of concentration are clear: the ability to achieve decisive results with finite means, to multiply the effectiveness of effort, and to shape outcomes against the odds. Yet these benefits are always counterbalanced by the risks of overextension, vulnerability, and unintended consequences. The future of force concentration will be defined by the interplay of old truths and new realities. As technology continues to evolve and the boundaries between physical and virtual domains blur, the challenge will be to harness the advantages of concentration, speed, power, and decisive action, while mitigating the vulnerabilities it can create. The enduring lesson is that concentration of force, in all its forms, is less about brute strength than about the intelligent and timely application of effort. It is a principle that rewards foresight, adaptability, and above all, the ability to marshal diverse elements into coherent and purposeful action. As we look ahead, the strategic and theoretical implications of this principle remain as relevant as ever. Whether on the battlefield, in the laboratory, or across networks of human endeavor, the art of concentrating force will continue to shape outcomes and define what is possible. The challenge for future generations will be to wield this power wisely, balancing ambition with caution, innovation with prudence, and the pursuit of advantage with the realities of a rapidly changing world.